We will now study measures of position. What does a doctor mean when she tells a mother that the mother's son is in the 90th percentile for height for boys his age? What is meant by that? Is that a center? No, it's not a measure of central tendency. Is it telling you about spread, how spread out the heights are for boys of the same age? No, it's not telling her that either. It's telling her a relative position where the boy's height fits compared to all other boys that same age. So when somebody says something like the boy is in the 90th percentile for height, that means that 90% of boys are his height or shorter, and that would then leave 10% to be taller. We are going to study measures of position here, and we're not going to work with percentiles in general. We're going to work specifically with the quartiles, which are specific percentiles, and we're also going to talk about standardized scores. With this first slide, we start with standardized scores. Jenna scored a 1540 on the SAT and a 27 on the ACT. Did Jenna do better on the SAT or the ACT? While the SAT and the ACT are not the same exam by any means, they both are used as predictors for college success. Colleges often use either or both of them to determine whether they should admit a student to their school or not. So we want to know, did Jenna do better on the SAT or the ACT? Do you think it's fair to simply say 1,540 is greater than 27, so that means she did better on the SAT? Certainly not. They're on totally different scales. The SAT has a specific scale and the ACT has a specific scale, but they're not the same. They're two different scales. So just because that one number for the SAT is bigger than the number for the ACT, that doesn't mean that she did better on the SAT. So how do we figure out if she did better on the SAT or if she did better on the ACT? Well, we need some information about those exams. If you look over here, we talked about the meaning of mu, which is a population mean. The population mean for the SAT is a 1500, and the population standard deviation, that means for all the test takers, population standard deviation is 250. For the ACT, the population mean for all people that took the exam is 20.8, and sigma, the standard deviation, is 4.8. That now gives us some information to think about whether Jenna did better on the SAT or the ACT. So if you notice, the 1540 is above the mean, so she scored above the mean on the SAT. She also scored above the mean on the ACT. She got a 27. But now we want to think about how much she scored above the mean. And because they're on different scales, we need to somehow standardize these scores. Hence, however, we get into standardized scores. So if you look at this, let's look at the standard deviation. Did Jenna score a full standard deviation above the mean on the SAT? If you added 1500 and 250, you get 1750. She did not score above 1750. She was much closer to the mean itself. Whereas down here with her 27 on the ACT, if you were to add one standard deviation onto this, you get 25.6. And she still scored above that. So she scored more than one standard deviation away on the ACT, and she did not score more than one standard deviation away from the mean, that is, on the SAT. So she essentially did better on the ACT. But we need to formalize this idea of figuring out how many standard deviations away the score is from the mean. This is what we call a z-score. The z-score of a raw data value tells you the number of standard deviations the data point is from the mean and the direction from the mean. So we want to measure how many standard deviations away from the mean a particular score is. And to do that, we have these two formulas. The z-score is the data value minus the sample mean divided by the sample standard deviation. Or if we're talking about population data, the z-score is the data point minus the population mean over the population standard deviation. So they're really essentially the same thing. One's just using the language of samples, the other is using the language of populations. So let's go ahead and compute Jenna's z-score for each of these exams. On the SAT, she's got a z-score of, and we'll put sub SAT here to let you know we're talking about the z-score for her SAT score, is her actual data value, x, is 1540, minus the population's mean for the SAT is 1500, over the standard deviation, which is 250. So Jenna's z-score corresponding to her SAT score is 40 over 250, which divides to give you 0.16. She had a z-score of 0.16 on the SAT. That means she scored 0.16 standard deviations, and since that number is positive, above the mean. And we already knew that because the 1540 was above the 1500. So she scored 0.16 standard deviations above the mean. Let's find her z-score on the ACT. On the ACT, her score was a 27, that's the x, minus the mu, which was 20.8, divided by sigma, which is 4.8. This gives you 6.2 divided by 4.8, and 6.2 divided by 4.8 is approximately 1.29. So Jenna's z-score on the ACT is 1.29 standard deviations above the mean. Again, it's above because it's positive, and you already knew that because we saw 27 is greater than the mean of 20.8. So this is how we can standardize the scores. We can now compare them when we talk about how many standard deviations they are away from the mean. With the SAT, she's only 0.16 standard deviations above the mean. With the ACT, she's 1.29 standard deviations above the mean. Since the 1.29 is greater than the 0.16, or in particular, since the z-score of her SAT is less than her z-score on the ACT, this means she did better on the ACT. Z-scores are something that we will use throughout the course. They're very important for you to learn. Let's summarize a bit of information about the standardized score known as a z-score. There are other types of standardized scores, but we will specifically be looking at z-scores for now. So if z is less than 0, what does this mean about your data point? Well, in order for this fraction, or this, doesn't matter which one you look at, in order for the z to be negative, this standard deviation is positive, so the only way this fraction can be negative is if this numerator is negative, because a negative divided by positive would be a negative, and the only way this number is negative is if the data value x is less than mu. So that means if z is less than 0, then the person scored, or the data value is below the mean. So this doesn't always apply to test scores. So let me just say, then x is below the mean. So the z not only tells you how many standard deviations the x value is from the mean, but it also tells you the direction, whether it's above or below it. So if z is less than 0, then x is below the mean. What if z is 0? Well, the only way you could get this fraction to be 0 would be if you had the numerator be 0. And the numerator is 0 when x and mu are the same thing. So that means the x is exactly the mean. So if z is equal to 0, then x is the mean. And finally, if we get a positive value for z, like we saw in the previous example, this means the data point x is above the mean. This is a brief introduction into standardized scores. They will play a much bigger role in the course later.